Hi everybody. In this lesson we're going to go over the integral test and the p-series test for determining if a series converges or diverges. So let's take a look at the integral test first. So this is theorem 9.10 in your text, and it makes this statement. If you have a positive function f that is continuous and decreasing, that is very important, it has to be decreasing for x bigger than or equal to 1, and you have a sequence an that matches up with the function f at integer values, then the series involving the an terms and the integral from 1 to infinity of f of x do the same thing. They either both converge or they will both diverge. So if the integral exists, converges, then your infinite series will also converge. Or if your integral from 1 to infinity diverges, does not exist, then your infinite series will diverge or not exist as well. So they both do the same thing. Now keep in mind, this test is only determining if this series converges or not. It's not actually evaluating what it's equal to. So if you recall back to the prior section, we did have some series that we could actually evaluate what they were exactly equal to, but those series had to be of one of the form either a geometric series or they had to be a collapsing series. There are many series that don't fall into either of those categories, and so we may not be able to actually evaluate what they're equal to, but we can at least determine if they converge or not, and if they do, then we could perhaps approximate what they're equal to. So this test only determines if the series converges or not, but it doesn't actually find what it's equal to. Now what we're going to do is we're going to just go over some examples showing you how to use this, and then at the end of this lesson we'll actually go over the proof of this result. So let's take a look at this example. So let's consider the series from 1 to infinity of 1 over n squared plus 1. Now keep in mind what this is actually equal to is if we put 1 in for n, remember this is going from n equaling 1 to infinity, if we put 1 in for n we get, and if we put 2 in for n, 3 in, 4, 5, and so on. So we want to determine if these numbers here add up to a finite number. So that'll determine if this series converges or not. So what we'll do is we're going to consider the integral from 1 to infinity of 1 over x squared plus 1 dx. Now let's just check that this actually satisfies the conditions of theorem 9.10. So my function f of x is 1 over x squared plus 1. This is a positive function. It does match up with 1 over n squared plus 1 at integer values. So remember, these are the an's here. So the an does equal f of n. That's certainly true. We also need to verify that the f of x is actually decreasing. So note that the derivative of this function, if I use the quotient rule here, it's going to be bottom times derivative of the top minus 1 times the derivative of the bottom, which is 2x, over, and so we get, which is certainly negative for all x bigger than or equal to 1, and so this is a decreasing function. so we can apply the integral test. So in other words, now we're going to determine if this converges or not. If it does converge, then our series converges. If, on the other hand, if this diverges, then our series will also diverge. So let's evaluate this and see what happens. So now this quantity, remember what we have to do is put a b up here in this infinity and write it as the limit. Alright, and now the antiderivative of 1 over x squared plus 1 is the arctangent. Alright, so now we've determined that this is equal to the limit as b goes to infinity, arctangent of b minus arctangent of 1. Now what is this quantity right here as b goes to infinity? Well, you have to remember what the graph of the arctangent looks like. Remember, graph of arctangent looks like this. Remember, it has these limiting values as you move towards positive and negative infinity, the limiting values being pi over 2 and negative pi over 2. And so this quantity that we have circled here is going to be pi over 2. You see, as we move towards infinity, the graph of the arctangent is approaching this limiting value of pi over 2. And so this quantity is going to be pi over 2 minus the arctangent of 1. Oh, that's a finite number. It's actually pi over 4. And we get pi over 4. Alright, now that's what the integral is equal to from 1 to infinity. And so that exists. So this quantity right here converges. This converges. Therefore, our infinite series converges as well, and we've determined that it does exist. Now keep in mind, this quantity, the series, what these numbers add up to, is not pi over 4, not necessarily pi over 4. In fact, it's not going to be pi over 4 in this case. All we've determined is that it exists. We don't know what this actually sums to. All we know is it exists. The pi over 4 corresponds to the integral, not the infinite series. But the pi over 4 does tell us that the infinite series does exist. We just don't know what it's equal to. Now, also keep in mind, when we're doing this limiting process right here, you could do this sort of in a quick manner where when you evaluate this, you could just think of this as being the arctan of x evaluated from 1 to infinity, and so this would be the arctan of infinity minus the arctan of 1. And you just have to think, okay, how do I properly interpret the arctan of infinity? Well, we interpret that as being pi over 2, because if we think of this value right here as being a b and letting it slide towards infinity, this quantity is approaching pi over 2, so we get pi over 2 minus pi over 4, and this quantity exists. Okay, so you can do this instead of writing out the limit as b goes to infinity. You could do it in a little quicker way like this if you want to. Alright, so that's how we use the integral test for this example. Let's take a look at another one. Let's look at our what we called our harmonic series before. Just a simple sum of 1 over n. Now keep in mind this is 1 plus 1/2 plus 1/3, and it just keeps going like this. So do these numbers add up to a finite number or not? Well, let's employ the integral test. So if we look at the integral from 1 to infinity, okay, so my function f of x, the f of x's are 1 over x in this case. Now just check, this is going to, you can easily see this is going to be a decreasing function. There's no problem there. But if you wanted to check, notice that the derivative is negative 1 over x squared, and that's certainly negative. So our function is a decreasing function, and it does match up with the an terms at integer values. So let's evaluate this and see if it exists or not. If it exists, then this will exist. If it does not exist, then this will not exist. So now evaluating this, alright, there we go. So of course it's just the natural logarithm of the absolute value x, and we get limit now. As b goes to infinity, the natural logarithm of b also goes to infinity, right? This is going to infinity, and this quantity right here is just 0. So what we end up with here is infinity. So in other words, this quantity here does not exist. So that means that our infinite series up here does not exist either, so this quantity diverges. So therefore, this quantity diverges, or does not exist. And it's interesting to note that if we look at the an terms, notice the limit as n goes to infinity of the an terms, it does equal 0. However, our series still diverges. If you think back, we had a theorem that said if our series converges, then the limit of our an terms must be 0. But we see that we can't go backwards. Just because the limit of the an terms is 0, that does not mean that your series converges. That theorem only went in one direction. Once again, that theorem said if your series converges, this implies that the limit of the an terms is 0. But we can't go backwards. We can't say if the limit of the an terms is 0, then our series converges. This is a counterexample to that. This shows that we have a series where the limit of the an terms is 0, but our series still diverges. It does not converge. So here, for this example, let's determine the p-values p for which this quantity, the summation 1 over n to the p, converges. Now keep in mind what this series represents. This is going to be 1 over 1 to the p power plus 1 over 2 to the p, and so on. So do these numbers add up to or for what values of p will these numbers add up to a finite quantity? Alright, so what we're going to do is we're going to invoke the integral test, and let's consider this result that we had previously back in chapter 8. So note that If you recall, we had this result. So this quantity equals, remember, 1 over p minus 1 for p larger than 1. So this quantity, this integral, exists as long as the p is bigger than 1, but it does not exist for p less than or equal to 1. So remember, if we put 2 in here for p, for example, then we're saying that the integral from 1 to infinity of 1 over x squared dx equals 1 over 2 minus 1, or just 1. So, because of this and the integral test, we now see that this quantity up here will converge for p larger than 1, and it will diverge for p less than or equal to 1. And that's the result that we have. So therefore, so that converges for p larger than 1, and it diverges for p less than or equal to 1. All right, let's take a look at one more example, and then we'll look at the proof of the integral test. So let's take a look at this series. And let's determine if this series converges or diverges. And whoops, this should go from 2 to infinity. I can't put 1 in here because the natural log of 1 would be 0, and I would be dividing by 0. So the n goes from 2 to infinity. So we're going to employ the integral test here again. So our function f of x is going to be 1 over x times the natural log of x. And that's going to be for x greater than or equal to 2. It's okay if we go from 2 to infinity instead of 1 to infinity. It doesn't really affect anything as far as the validity of the integral test goes. Now this will be a decreasing function. You can easily verify that. Just note that the derivative is equal to this. So here's our derivative. It's negative 1 plus ln x over x squared times ln x squared. And certainly this is going to be a negative quantity because of this negative right here, and everything in the numerator and denominator being positive for x bigger than or equal to 2. So this is a decreasing function, so we can employ the integral test. So let's take a look at the integral from 2 to infinity now. All right, now what we're going to have to do here is we're going to have to do integration by substitution. We're going to have to let the u equal ln x. That's the trick here. So if I let u all right, so you see then this quantity becomes, now if I put 2 in for the x here, that means the u is going to be the natural log of 2. And if I put infinity in for the x, the natural log of infinity is infinity, and so the u will be infinity as well. Now, the 1 over x dx, that's going to become du, and then I have 1 over u here, so this is going to become And so this is equal to the natural log absolute value u evaluated from the natural log of 2 to infinity. I'm just doing the quick way. Instead of putting a b up here, I'm just going to put an infinity in here and interpret it that way. And so this is going to be the natural log of infinity minus the natural log of the natural log of 2. Now the natural log of infinity we interpret as being infinity, and this is just some number here. It doesn't matter what it is really. It's just some, I'll call it c for some constant number. And so this quantity is equal to infinity. Okay, infinity minus a finite number is still infinity. So therefore this quantity does not exist, which means that this up here is the same as this. We just did a substitution. Does not exist. And so by the integral test, this infinite series up here diverges. All right, now let's take a look at the proof of the integral test. So let's go over that. So here's the statement again of our integral test, and we're going to use some graphics from the book to help us out with the proof here. Now notice the integral test makes a statement that the infinite series and the integral either both converge or they both diverge. Now that is the same as saying this. That's the same as saying if the series converges or exists, then the integral will exist or converge. And if the integral converges, then the series converges. Okay, so this theorem is really saying two things. It's saying if the series converges, then the integral converges, and if the integral converges, then the series converges. This is the same as saying the series converges if and only if the integral converges. So what we really need to do here is prove two things. We need to prove number 1 and number 2. So we need to prove two if-then statements. Now let's take a look at the proof of, let's do number 2 first. So we're going to prove that if the integral converges, then the series converges. Okay, so we're going to prove that first. Well, to help us out with that, let's take a look at this graphic down here. So down here, we have a graph of our function f of x. And you notice these little rectangles that are inscribed underneath the graph of the function. Well, notice that the area of this first rectangle is actually a2. This height, the height here, is a2 times the width, which is 1. And so this area is a2. The area of this next rectangle would be the height, which is a3. That's the same as f of 3 times the width, which is 1. So this area is a3. And the same thing for this rectangle, a4, and so on all the way down. And this one down here we have an. So you see from this graphic, because we inscribe the rectangles under the graph of f, and remember the integral of f is the area underneath the curve of f, we then have this result. From this graphic, we see that So this quantity, the area of all those rectangles, is less than or equal to the area underneath the graph of f from 1 to n. And of course this quantity is going to be less than the integral from 1 to infinity of f dx. Right? Now this is true for all n. And you notice that this quantity right here is equal to our nth partial sum, but we're missing the a, the very first term, a1. So this quantity right here is equal to Sn minus a1. So what we now have is this result that Sn minus a1 is less than the integral from 1 to infinity of f dx, and that's true for all n. Now moving the a1 over to the other side, we get this. And this is true for every n. So therefore the nth partial sums are an increasing sequence that are bounded above by this number m. So if you have an increasing sequence that is bounded above, remember we discussed a previous result back in a prior section that said then the limit as n goes to infinity of the Sn terms must exist. Right? You have an increasing, the Sn's are increasing, they're bounded above by m, and so the limit as n goes to infinity of the Sn's must exist. And that's from a previous result that we discussed. So that proves the first statement number 2, that if the integral from 1 to infinity of f converges, then the series must also converge. Let's look at the statement number 1 and prove that one now. So this is a pretty interesting proof because all we're going to do is change the way we draw our picture down here. So now we're going to prove number 1. And so we're going to prove that if all right. Now the way we're going to prove this one is we're actually going to prove what's called the contrapositive. Notice that this statement is the same as saying, if the integral does not exist, then the series does not exist. That's called the contrapositive. So this is the same as saying if this diverges, then the series must diverge. Okay, that's the same thing, right? So we're saying if the series converges, then the integral converges, is the same as saying if the integral did not converge, then the series could not have converged. So this is called our contrapositive. Remember the example I had discussed previously illustrating that. If I made the statement, if I'm washing my car, then it is sunny outside. If you think about it for a minute or two, you'll convince yourself that that's the same as saying if it's not sunny outside, then I will not be washing my car. Right? So if I'm washing my car, then it's sunny outside. Same as saying if it's not sunny, then I'm not going to be washing my car. So we're going to attack number 1 by proving the contrapositive. Now to help us with this, consider the picture down here in your text we're going to draw these rectangles a little differently down here. We're going to draw them like this. So they're above the graph of the function f. Now notice that the area of the first rectangle here is going to be a1. The height here is a1. This is f of 1, which is a1 times 1. So, and the area of the second rectangle then is going to be a2 by the same reasoning. You see this height right here is f of 2, which is a2, times the width, which is 1. So this is a2, and then a3, and all the way down to this would be an minus 1 right here actually. The area of this rectangle would be an minus 1, a sub n minus 1 times 1. Alright, so what we have then based on this picture, now you see how the area of the rectangles, if I add all of them up, they're larger than the area underneath the graph of the function f. So what we then have is this result. Give myself a little bit of room here. So based on that picture then, we have the following result. Okay, so we see that a1 plus a2 plus dot 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 plus a sub n minus 1 is actually bigger than or equal to the area underneath the graph of your function from 1 to n. That's what we just reasoned in that graphic. If you want to see that again, just rewind the video and take a look at that again. Now, so what we have here, this would be our nth partial sum here, or n minus 1 partial sum. And so we see that that is bigger than or equal to this quantity. However, we're assuming that the integral from 1 to infinity of f of x is diverging. So what's happening now for the right hand side here, then if this diverges, that means that the limit as n goes to infinity of the right hand side must be infinity. So this quantity is infinity because we assumed that the integral from 1 to infinity of f of x dx does not exist, so it diverges to infinity. So therefore this limit must be infinity. And so therefore the limit of the nth partial sums here must be infinity as well. And so it doesn't really matter whether I have an Sn minus 1 here or an Sn. The n's going to infinity. Doesn't matter what I put down here. So therefore the limit as n goes to infinity of the nth partial sums is infinity as well. And then that proves that the summation must diverge because the nth partial sums diverge. The limit of the nth partial sums diverges. And so then we can say, therefore, down here, the summation of our a_n's diverges. Alright, and so that concludes the proof of the integral test. It's just a very interesting proof because, as we can see from the graphics, it all depends on how you draw your rectangles, whether you draw them under the graph of your function or above the graph of your function. So that concludes our lesson now on the integral test and the p-series test.